We're back in class again. I want your cameras on when we're in class. I need to see you as well as you see me, and we all see each other. That sounds like almost a Beatles song. And we all see each other. Okay, so schedule. Today's class is machining. We do have a recitation. It's going to be on sustainable materials, and we might have an extra credit topic in addition to that. What's scheduled is where do your materials come from and how do you produce, use, and reuse them sustainably? Very important for our footprint. And again, there may be an interesting additional topic.
Neil, should we have like the last song before class?
Oh, let me switch. Yes, I would love to have a final song.
The final song, here you go.
A og B, spott og spé, grísinn galar upp í tré, hróp og köllum víðam öll og þá sagan öll. Lamb í baði, borðar súkkulaði, hundur jarmar, galagrísinn hátt.
Okay.
So, what's the translation?
Okay. So the kids, they sing his song, but we use it also as a marketing tool. We let them also have not only candy, but also like fabulous Fridays, because we have like open days. So then they come here also on the Fridays, on the open days.
But tell us, what is the translation of the song?
It's
A and B.
no, it's
Spotty's B.
so it's a song. It's a song. It's a
In Astrid Lindgren. It's from that.
from like adventure books that they're singing song from. It's about like animals and their sounds and so on.
Okay. Well,
Yeah.
I think they should get candy.
Yeah, they will get double version. Thank you.
Okay.
Thank you. Bye-bye.
Thank you. Okay, back to class. And again, I'm a broken record, but I'm looking at too many icons of names. If you're in class, I need your camera on. We need to see each other. Class doesn't work if we just see names. We need cameras on. Maxime, Rudolph, Hariharan, Matthias, Sanjay, Yaran, Praveen. Okay, so on to machining. This is a dramatic, exciting, and challenging week. We're going to cover making big things. So larger forces, larger materials, much more important safety. And here's in the chat is the translation. The piglet is happily croaking high in the fir tree. A mouse is sneaking into the house. She wants to get a sniff. A lamb is quickly croaking chocolate. A little pig is croaking, a lot of croaking. Here's one of the most impressive assignments from this week. This was Sam, who we'll encounter a few times. And he made this boat. And there's much more to say about how he made the boat. But this was a dramatic assignment for this week. So we're going to cover how you make big things. So things on the scale of furniture around you. Depending on your lab, typically you'll get a 4-foot by 8-foot sheet of plywood with a machine that size, and you'll make big parts. So it's like what we did in laser cutting, but on a huge scale. So some examples, this was a student in the class who made a standing desk and turned it into, um, spun it off as a business. Let's see, it's, so his girlfriend wanted a standing desk, and uh, here she is with it. And let's see, I'll update that link. But this is a classic assignment for the week, starting from the sheet stock and cutting out all the parts to make the desk. This is nicer wood than you'll likely start with. But that's one example. In that lineage, Open Desk is a platform for open furniture. Here are lots of examples. At Fab is another platform. So those are examples of furniture, and then it can get bigger. So this is a project making rapid shelter for things like emergencies. This is a project a colleague made using the tool you're likely to be using to make a whole house for the Museum of Modern Art. WikiHouse is using these tools to make full-scale houses this way. This was a small house made as a Fab Lab project. And then this was the biggest Fab Lab project ever. This is a full-size house made, including all the furniture in it, all using the skills we're going to cover this week. So you won't be able to make a house this week, likely. Well, maybe a tiny house, but it's just using more of the skills we're covering. So start with the tools. On the smallest size, this is a machine made by a former student. And a router cuts out 2D shapes, but this has a computer vision, and so you do the coarse motion and it does the fine motion. This isn't good for making giant things because your arms can't reach, but it's good for making fine parts. And in particular, what's great about the shaper is all the other tools, you bring your stock to the tool. With the shaper, you can bring your shaper to the stock. So you can engrave in a floor. You can bring the tool to wherever it's needed. So that's the smallest tool. Maslow is an interesting offshoot. This, instead of having a big gantry, has tendons. And so you have anchor points, and then the tendons pull this head around. So instead of a giant machine, you anchor it on the stock. And then the classic machine for this week is a ShopBot. This was founded by a colleague who works very closely with the Fab Lab network. And so a classic ShopBot is 4 feet by 8 feet. They can be both open and closed loop, and I'll talk about that. And so these are in the range of $20,000 to $30,000. And they're fairly stiff, but they're bolted together, so you have to periodically update it. Then a machine like this, the Onsrud, this goes from $20,000 or $30,000 to, let's see, their site's not loading, but $100,000. And the difference between the ShopBot and the Onsrud is they can basically do the same thing. The Onsrud is much stiffer, and so you can machine more aggressively and more continuously, and you don't need to periodically readjust it. Then there are tools like Haas or Herco. And so let's see, this is a machine tool in my shop. This cost about $300,000. And it has a fairly large work volume. It can move in 5 degrees of freedom. So it moves X, Y, Z. The bed can rotate and then the head can rotate. But this is much, much stiffer. So the ShopBot can do light metal like aluminum or brass. The Herco can do titanium and stainless steel at high speed. But you need a much stiffer machine and a much heftier spindle. Then while we're touring machines, the Zund like this, that came up today at the Kerala Fab Lab. The Zund, depending on the model, is maybe $100,000. And so it's got a very high-speed machining spindle that's very accurate, that it's laser trimmed. But what makes this one special is there's a moving vacuum bed. And so you can work over a large area quickly, and you can machine, and you can also cut with heads that roll or punch or shear or cut. And so this is used for high-end advertising displays, for race car composites, for luxury leather goods, or all sorts of unusual uses of this giant flatbed cutter. And then a really interesting machine you'll hear about in the machine building recitation is Jens in Norway has been making machines that are, let's see, we want to go to the Humphrey. This is a machine on the scale of the primary machine for this week, but this is an open design made in the lab, and in particular, most of the parts of the machine are made on the machine. And so he's made a series of a parent machine, a child machine, and a grandchild machine. And so if you get really excited, later when we cover machine building, we'll cover how you can actually learn to make these machines. So most likely in your lab, you'll have a ShopBot or an equivalent, a large milling machine. So you have the machine, then you need the materials. And an interesting one to start that's easily neglected is cardboard. So not ordinary cardboard, but you can get like trifold cardboard that's thicker, and you can then cut that to make things like beautiful furniture out of cardboard. You can machine this. It doesn't really machine well. It really wants to be cut with an active driven knife. So it's a note that you can use heavier duty cardboard to make a killer app for it is furniture that's lightweight, low cost, recycled, renewable. Foam machines easily. And so let's see. We look at so this is used to insulate buildings. Loading slowly. This rigid foam, but it machines very quickly. And when we get to molding, so you can use that to make forms in it. And a killer app for that is you can make molds for making very large architectural casting. And the main thing we're going to be using today is plywood. So when I showed you David's desk, that was made in veneer plywood. That's layers of wood laminated. That's the nicest looking wood. It's fairly expensive. A 4x8 sheet of that can cost $100. there's MDF, which is short wood fibers in a resin matrix. It has much worse structural properties. It's heavier, it's not as strong. And depending on the resin, it can also be unhealthy to be around because the resin can outgas vapors. There's what's called green MDF that's more friendly. But what's good about MDF is it machines much more smoothly. And so it's used, for example, for billboards. When you put up a billboard, you want a very smooth surface to put it on. And you can machine MDF when you want to do 3D machining in wood with very smooth surfaces. MDO is a combination of the best of both. It's a veneer core with an MDF overlay. And then the real workhorse for this week is OSB. OSB is sort of literally the sausage or the hot dog of wood. So sausages or hot dogs are made by kind of sweeping up lots of parts, and you probably don't want to know what goes into a hot dog. And that's what OSB is. OSB is chunks of wood that are left over from all the other processes stuck together. But what's good about OSB is it has pretty good structural properties because it's real wood. It's not quite as good as veneer, but it's pretty good. But it's really, really cheap. So it can be $10 or $15 for a sheet of OSB. And so one use of it is it's just very low cost. It's used like when you have to board up a building if a window breaks. It's not that popular because it's rough. It's not as smooth as veneer. It doesn't have as beautiful a finish. But what I'm showing here is after you machine OSB, you can sand it and then you can coat it. And so you can actually make really nice finishes in this very low cost material. But beautiful veneer wood just looks beautiful right out of the gate. OSB, you need to sand it and seal it and finish it, but it's underappreciated. You can make really nice things out of OSB, and it's making great use of all the available wood. And so, most likely, depending on what's locally available, let's see, Ricardo's noting the thickness is very unpredictable. I'll talk about joints for it. So typically, depending on what's locally available in your lab, you'll have a 4 by 8 foot sheet of OSB on a large format machine. So OSB is often used for the packaging of the machine, Shaheen notes. HDPE we sometimes use in machine building. It's the material of cutting boards. It machines really easily. I'll talk about this picture when we get to machine building, but this is machining high density polyethylene. Then polycarbonate or Lexan, or sometimes referred to as bulletproof glass, is a really hard, tough polymer. So unless you have a extreme laser, you can't laser cut this, but it's pretty straightforward to machine it. So you can machine polycarbonate to make like very high impact materials. Garolite is like a composite, but unlike glass or fiber composite, that's dangerous, and I'll talk about that later. This is a fiber reinforcing that makes it very easy to machine, but it's a very stiff material, so it's very easy to machine garolite sheets. And then you can machine aluminum, and in particular, you can get a material like Highlight, which is an aluminum cladding around a polymer core that makes it lighter, can be lower cost. It machines really easily, both for flat parts, and you can fold it to make folded parts. And in fact, Boy, I'll see if I can find it. My students use that to make an amazing art installation. Let me. I'm going to take a look quickly to see if I can find it. Oh, great, I found it, and I'll add a link to this. So, one of my students, let's see, that's not loading properly. So let's go back to here. So these are art pieces, the size. Okay, oh great. This is the picture I wanted. Let's see. I'm going to interrupt again. Jasmine, Charing, Tangam, Manikandan, Alex, Shivraj, cameras, Pradeep, Armando, cameras on if you're in class. I don't want to teach the class to a bunch of just names. I need to see people. So these pieces are the size of an atrium. This is the aluminum composite. And then, believe it or not, these were made in an afternoon. So these were done on the Zund, but you could also do them on a shop bot. And he milled out the shapes, and then he milled notches to make shapes to fold these. And so these architectural pieces were done, in an afternoon of machining and then assembling it at this large scale. And there's interesting math that went into how you design them, but this is an inspiration for going from sheet stock to large scale. So you'll need to pick the material. Most likely you'll start with OSB. You'll need to buy the material. And here it's very strongly locally. So the metal and the plastic, you can buy any of these in the US from McMaster Carr, but it costs much more expensive. For the plastic sheets, we go to a plastic vendor like US Plastics. For the metals, this is very local. So yeah, Jacob is asking about folding plywood. Jacob, I'm going to talk about that. So in Boston, Admiral Metals is a local metal vendor we work with. Likewise, we have a local vendor of plywood who works with contractors. And an important thing to know about these vendors is they supply on industrial scales, and what they have always changes. And so often what they consider scrap left over after a big job is your whole project. And so buying from them is more than just a standard stock where you buy the same thing. You stay in touch with them and check what's available and design around their supplies. And so in each part of the world, you want to find the local metal and wood vendors to work with for sourcing. They're not global, they're very strongly local. So you're going to make the project this week, and like PCB board houses, if it's successful and you design furniture and then you want to reproduce it, there are job shops. So Proto Labs is a really handy one, and Proto Labs has every possible process. So molding, they have all the different kinds of machining as well as printing and sheet metal. And you send them a job and they produce it. The next week when we do electronics production, we're going to meet the PCB houses. And initially they just did PCBs. They expanded to 3D printing, and now they've expanded to 3D machining. So you can send them a design and have them do your machining. And then a number of these are distributed. And so what these ones do is, rather than having a central factory, This is a whole network of local shops, and you send your work out, somebody bids on it, and it gets produced locally. And it could be an interesting thing to build something like that for the Fab Lab network, to use the Fab Lab network as a job shop. But these are commercial versions of distributed production. So let's say you're going to make a desk, and you have a shop bot, and you have a piece of plywood. The next thing you need to do is pick out the tooling. And so in the Fab inventory, all of these are tools that we're going to use. There's a very wide range. There isn't a single choice. So the first distinction is a drill bit drills a hole and comes to a point. An end mill is very different than a drill bit. The drill is only designed to cut down. The end mill is designed to cut on its side. It's designed to go horizontally as well as vertically. So we're going to be using end mills. There are router bits. And so router bits like these cut on the side, but they're only designed to go in 2D. So you use these, for example, to cut out the edge to shape the edge of a piece of plywood. They're not designed to make arbitrary 3D shapes, whereas end mills, we work in arbitrary 3D. So then for the end mill, they vary. So this is a 2-flute end mill. If you look, there's 2 spirals. Most common are 2, 3, or 4 flutes, but you can go down to 1 and up to 6. I've seen. When you have more flutes, each one takes a smaller bite that gives you a smoother finish, but there's less room to remove the chips. So you use fewer flutes when you're removing a lot of material. You use more flutes when you're finishing and you want a smooth surface. Let's see, if we go to a source I buy tools from is Carbide Depot. And so if we go to end mills, their site is running slowly. Let's hope this, okay. So once you go to the end mill, so here we're picking the number of flutes, and I'll come to the shapes. But then one more thing you have to pick is here, if you look at these, they're slightly different colors. What's going on here is, for a little bit more money, not much, they grow a ceramic layer on the surface of the tool, and that significantly extends the lifetime of the tool. So typically you always go with a coated end mill. Then the next distinction is, if you look at the tip of the end mill, if you look at the front of the end mill, actually, yeah, this is a good image. If actually, that's a little confusing. So if this is our end mill, and then we have the flutes, there's 2 different kinds. In one kind, they don't meet at the middle. The other kind, they meet at the middle. This kind is called center cutting because you can go down as well as over. This kind is not center cutting. and so you can't plunge with it. I'll talk about how you use it when I get to the toolpath. Non-center cutting does a better job of removing chips, which is why they exist. Center cutting lets you plunge. And so typically we are always using center cutting end mills. Yeah, Ricardo is noting there is a matrix of which coating works with what material, which is why there's multiple coatings. The next thing you need to pick is up versus down cut. So here's a sheet of plywood. If you're milling with the end mill, and if the spirals are going this way, when the tool turns this way, it's trying to lift up the top, and so you pull up an edge on the material. If instead the flutes are going this way, here's the end mill turning, this is pushing down, and so you get a clean surface on the top. But the problem is there's nowhere for the chips to go. You're kind of pushing them into it. It's the opposite at the bottom. This one at the bottom gives you a clean surface. This one at the bottom will be ripping the surface out. So a common thing to do is you can start with a shallow cut with a down cut end mill. And then once you have that, you finish it with an upcut end mill. Or you can get what are called center cutting end mills, where you have flutes going one way and then they meet flutes going the other way. And so if you come in from the side, let's see, I drew that backwards, not that it really matters. But if you come in from the side, the top is getting pulled down and the bottom is getting pulled up. So you have to pick upcut versus downcut for the direction. And then there's still more. We go back to end mills. So you'll see there are regular end mills. There are ball nose end mills where the tip is curved rather than flat. And I'll talk more about that when we get to machining for mold making. But if you have a curved surface, and if you machine in layers, a flat end mill will give you steps, whereas a ball end mill can give you a smoother undulating surface. However, depending on how you use the tool path, you can get a smooth surface with a flat end mill. But a more important difference is if you need to get into a pocket, the flat end mill might hit the edges where the ball end mill can get in. And so ball end mills tend to get used for finishing cuts for smooth surfaces and getting in for finer features. And then in addition, there are a number of other specialties like extra long end mills that can get into a narrow pocket, but these you have to go very slowly because they bend easily. And then there are tapered end mills that can make a fine end cut, but are stiffer. There's tiny end mills for the littlest features. And so there's a huge range of tools. And so part of this week is going to be picking out the tooling. Yeah, so the flat, sorry, Stephen, what's the question? A flat bottom end mill makes a flatter, is best at making smooth surfaces and at chip removal. So a big part of this week, one part is picking the tooling. Then the next task for this week is what's called speeds and feeds. So this is a Bible of machining called the Machinery's Handbook. And let's see, another site loading slowly. You should have, hopefully that'll load. This is a handy book you should have in your lab by your machine tool. That's a really good reference. Speeds and feeds has to do with, let's see, Stephen, you're talking about,
Yeah, straight flute rather than upcut or downcut. Some of the sawmill forum sites, they say that these give you good top and bottom surface finishes.
oh, interesting. Flute and mill. Yeah, I'll mention that in the link. I haven't used them. I've been happy with these alternatives. I'd be interested in anybody's experience. I haven't used these.
Carpenters in Germany use those a lot as well. They're
Okay.
also easier to shop.
Yeah, I mean, these are great for chip clearing. There's lots of room around it. So these are great at getting the chips out. So feeds and speeds. The chip load is, think about the tool with this flute making a bite. So the tool is spinning, it's cutting, but then the tool is moving. So each time around, it makes a bite. And the chip load, it's a function of how fast it's spinning, how big the flute is, and then how fast it's moving. And a rough guidance is, excuse me, between 1 and 10,000 inches is a typical chip load. So the feed rate in inches per minute divided by the revolutions per minute times the number of flutes is how much each bite is taking. If the chip load is too large, the machine will scream because you're putting too much force on it. But it's actually bad to have a chip load too small. The tool has to cut. If the chip load is too small, you're kind of rubbing. You're not really biting into it. And so there's a chip load where it's happiest. The cut depth is when you make succeeding passes, how deep you go. And a rough rule of thumb is, if this is our tool, the depth you go is on the order of the diameter of the tool. So for a larger tool, you can have a bigger cut depth. Then the step over is, let's say this is the edge we want. If the tool goes on this path, and then the next one goes on this path, from the side view, you'll get a little bump at the boundary between them. And so the step over is how much you overlap succeeding passes. And it can range from 0 for rough cutting to 90% for very smooth finish cutting. Lubricants, you're not likely to use this week. So when you machine stainless steel at high speed, there's typically a lubricant, and it's doing two things. One is it's helping lubricate the tool, helping it move. The other thing is it's helping remove heat from cutting. You don't use lubricants with wood. You don't typically use them with plastic. And for light metal machining, you don't need them. But for heavy metal machining, you use lubricants. Then an interesting thing you can do is this is abrasive grains. You can use them in a slurry to machine hard material. And then you can get, again, thanks to our friends in Shenzhen, these surprisingly affordable diamond impregnated bits. And these cut hard materials, not by making a flute making a chip, but by grinding away little tiny particles. And so an example of that is at the, oh, let me reload the page. I updated this link. Pilchuck is a leading glass retreat in America. And what we're doing here is, this is a diamond bit, and then this is a puddle. It's a boundary of clay, and we have a puddle. And the reason it's there is when you use the diamond bit, you need to cool it, but also the fine particles are hazardous to breathe them. And so here the puddle suppresses the particles made by the grinding. And what we're doing there is we're actually plotting in glass. We're machining 3D surfaces in glass that you can't do with an end mill, but you can do by machining with a grinding bit. Okay. Next comes fixturing, and this is surprisingly non-trivial. So if you want to buy a vise, not a visa, a vise, a simple bench vise might be $10 or $20. But if you want to buy a NC machining vise, let's see, let's see, I don't know if Amazon even, an NC machining vise might be $1,000. And so the $1,000 vise compared to the cheaper vise, it has much flatter surfaces that are smooth, flat, rectilinear, stiff. Oh, okay, yeah, toolmaker vise. So for precision machining, you can use a machining vise. For simple machining on a large format tool, you can use bar clamps. So these are just handy clamps to clamp it down. But you can't use those for big areas, because if you use a bar clamp and you clamp it at the ends, nothing is holding it in the middle when you machine. And so you need to distribute the holding force. So a most common way we do that is with screws. You can use a cordless gun, and you can pop in small woodworking screws. And then there are special nails for this purpose. These, if you use screws, it's very bad if your end mill hits the screw. These are nails made out of a polymer that you can machine right through them, and then you can get a special tool to pop them in. And so these are really handy. You put your piece of wood down, and then you just pop these in, and then that lets you distribute the holding force. You can use a vacuum bed. This is a project where somebody made his own vacuum bed. And so here the vacuum holds it down. And so in a job shop in production, vacuum beds are preferred because it's much quicker to get the material in and out. The only limitation with them is they need some maintenance. The holes get plugged, and so periodically you need to do maintenance on the holes in your bed. But production tools use vacuum beds to distribute the holding. When you machine wax to make molds, often there we use a bead of a glue gun to hold it, and then you just crack that to take it off. And for the most complex machining, where you're going to machine with all 5 axes. One of the interesting ways you do it is you take a piece of metal you want to machine, and then you take a low temp metal that's kind of like solder, and you cast your metal in a low temp metal. You put that all in your machine, and you machine through both, and then you melt away the low temp material to take your part out. So there are a lot of options for how you fixture. But typically we use screws or these sacrificial nails to distribute the hold down. Yeah, Ricardo is looking at mistakes were made in Mexico. So next up is, what does the nail go into? So you have the bed of your machine. You have your stock. So this is going to be machined and turned into a piece of furniture. In between those is a sacrificial layer. And so you cut into the sacrificial layer. And so if this is your large machine, periodically what you do is you put the sacrificial layer on it, and then you run a long job where you just go back and forth and you machine the whole sheet. And what you're doing is you want the machine to be flat in the coordinate system. You want the sacrificial layer to be flat in the coordinate system of the machine. And so you machine the sacrificial layer smooth and flat, and then you use that to hold down your sheet. And then depending on how often your machine is used, somewhere between months and years, you replace the sacrificial layer when it's used up. Then the other thing is, if you look at a tool like a ShopBot, it's bolted together, and over time, the bolts drift a little bit. And so to exaggerate, we have the rails on the side of the machine that the carriage is traveling on. But to exaggerate, they might not be parallel. They might be converging or diverging. And then we have the vertical axis of the machine, but it might not be quite vertical. And so what that means is when you cut out a square part, it might not be quite square. And so periodically what you need to do is run a test job of make a test part and check that when you send a square part in, it comes out square and the dimensions are right. Then when you're machining, you're making a lot of dust, and I'm going to talk about that for safety. You need to collect it. And so there's a boot on the machine that's vacuuming up the dust, taking it to a dust collector. It's noisy. You typically want ear protection. If you see dust coating surfaces in your lab, it's a very bad sign. You don't want to be breathing it. You don't want to distribute through the lab. When everything is working properly, the dust goes into the dust collector. If you see dust not getting collected, something's wrong, you need to address it. So then one of the questions in the chat, this is now the answer to it. You're going to start with a flat piece of wood. This is called a flexure, where you make lots of little beams, each that can bend a little bit. And by doing that, you can start with a rigid flat piece of wood, but make something that bends. And your ability to do that does depend on the quality of the wood. These aren't great in OSB because it's chunky. This works better with smoother veneer wood. And then this is called kerfing, where what you do is you machine not all the way through. So you have a continuous smooth outer surface, but you can bend it. And again, that needs better quality wood to do a good job. But with flexures and kerfing, you can make curving 3D shapes starting from 2D wood. Then steam bending is where you make twisty curving surfaces by putting the wood into a box that heats it with steam and softens it, and you fold it into a shape, and then it sets back. And then in turn, there's normal plywood. The plies are going in alternating directions to distribute forces. This is special wood where the plies only go in one direction. That makes it less good structurally, but makes it much easier to bend to make smooth, curvy surfaces. So you can use fasteners, nuts and bolts, but you should try to avoid it, and I'm going to talk about why. You can use glue, and so for wood, there's good wood glues, but you can't undo that. Much more interesting this week is joints. So, is the Kamakura Fab Lab connected today?
Yes.
Okay. So, Kamakura, this is the Kamakura Fab Lab, and it's in an old sake brewery.
Yes.
And this came out of a study of the Japanese wood joints. And so this beautiful page, every one of these is a different version of how you bring parts together to make a joint that transfers forces. They have different directions where the parts come in and different ways to hide the joint. And so there are hundreds of types of joints. This is a poster of types of joinery. And so in laser cutting, I showed you a few kinds of joints. In woodworking, again, there are hundreds of types of joints. If we go back to the laser cutting week, one of the nicest joints for this week is the pinned joint. So this last example here, a wedge joint like this, the reason this is such a handy joint is you have the part that go through, you put in the wedge, and you don't need to get the dimension right. You don't need to know exactly the thickness of your stock, because just if it's a little thicker or a little thinner, the wedge will go in a little more or a little less. But a wedge joint is a really nice way to handle the range of types of joints. Then once you have a joint type, there's a huge range of things you can do. So reciprocal frame construction is a joinery strategy where you take the joints and then you make these sort of structures out of them. These are called reciprocal frames. Tensegrity is a really interesting idea where you have strings that are good in tension, you have beams that are good in compression, and there's no flexion, there's no bending. It's all combination of tension and compression. And you can make what looks like beautiful floating structures with tensegrity. And then the Maxwell criterion, this is a classic paper from 1870. And it's an important thing to be aware of this week. If you make, say, a bookcase, and this is the bookcase, it'll be very wobbly because it can shear like that. So instead, in the bookcase, you typically have a reinforcement like that. And what's going on is you need to count how many degrees of freedom there are and how many constraints there are. And if there's more degrees of freedom than constraints, it's a mechanism and it can move. And so you need to add constraints so that you don't make a wobbly structure. And so that's called the Maxwell criterion. Okay, so now we have our machine, we have our stock, we have our tooling, we have our fixturing. Now we need to make a toolpath. So terms, we've already seen kerf, the idea that the tool has a diameter, and so we need to offset by the tool diameter to get the right shape. In addition, another important concept for this week is runout. Runout is because the tool might not be perfectly vertical and the bearings might not be perfectly vertical. If this is where you place the tool, it might meander a little around it. And so this is the diameter of the tool, but the actual cutout you make is larger because of the runout of the tool. And you need to know that in the design. Then the tool can either go this way or that way. This is called climb machining because it's trying to climb over the stock. This is conventional because it's pulling into it. Climb makes much more force on the machine, but it leaves a cleaner cut. Conventional, the spinning holds the tool against it, but it leaves a rougher cut. So it's common to use conventional to start and climb for finish. Then rough cutting is where you cut quickly in layers, and then finish is where you move all the axes, and that's rough. And here's finish making very fine steps. And so depending on whether you what you're doing, there's rough and finish cutting. Then there's a whole list of high-speed machining, dry, ramping, adaptive swarf, rest, trochoidal. These are more advanced strategies. So trochoidal is particularly interesting. In trochoidal milling, here's a paper on it. It looks really crazy. Instead of the tool just going in a straight direction, in trochoidal milling, the tool goes in sort of crazy loops. And what that's doing is in climb, the chip starts thick and ends skinny. In conventional, the chip starts skinny and ends thick. What trochoidal is doing is trying to make a uniformly shaped chip by moving the tool as well as spinning the tool. So those are more advanced tool paths. Then for this week, you'll likely cut from one side, but for more complex things, you might flip it over and machine on both sides. And to do that, you need to register. And then 2D machining is, in 2D machining, it's like laser cutting. You just make a path. In 2.5D, or in sort of 2.1D machining, you make a path, but you make multiple paths, each one going deeper. In 2.5D machining, you're machining in 3D, but only in flat layers. In 3D machining, you move all axes at the same time. And then if you have extra axes on your machine, 4D is you rotate while you machine, and 5D is you move all the degrees of freedom. Then the next thing you need to worry about is the tools we're using are might be, say, 1/4 of an inch. So let's say you want to make a joint. If you use a tool like that, it'll be shaped like this. And if you want to have a part that comes in here, it's going to get stuck there because of the shape of the cutout. And so we make things that look like this. And so what this is doing is, sorry, let me do that with more room. So if you cut out a shape like that, what that then does is a part coming in here can go all the way down because we made this extra space. So T-boning or dog boning gives you room for joints. Next thing you have to be aware of is there's the tool. It has the flutes. Typically, there's a shank on the tool. Then it goes into a tool holder, and then this goes into a spindle. Any one of these can collide with your part, so you need to make sure there's enough room for the tool to get in. Next issue is, let's say here's our big sheet, but let's say we're cutting out in our sheet a small part. When you get most of the way around cutting it out, there's nothing holding it, and it'll suddenly start flapping around. So one of the things you can do looking above is, if this is the part we want to make, you make little tabs you leave behind that hold it in place, and then you snap it out. Or side view, another thing you can do is machine almost but not all the way through. And this gives you what's called an onion skin. And then you can, just like with a knife, you can trim it out. So tabs and onion skinning help hold the part in while you're cutting it. Nesting is a key skill for this week. And I mentioned this for laser cutting, and it's more important this week. Nesting is how you place your parts to make good use of your stock efficiently. And so you can do it by hand. There's tools to automate it. A very important concept for this week is, when you start cutting, you might have the axes wrong. You might have the units wrong. You might make mistakes in making the toolpath. So initially, before you actually cut your material, we cut in the air. You move the tool away from where you're going to cut, and you do your job in the air. Make sure it looks good. Then you go back and cut it. Likewise, before you do the whole job, do a small test cut. Cut out a little part to make sure everything's working. Typically, the CAM software lets you simulate. And another thing you can do is prototype. It's a surprisingly good idea to laser cut a little cardboard version of the project you're going to make, or 3D print a kit of parts, put them together before you do the big job. So all of that goes into the CAM. And there, for example, the ShopBot comes with VCarve that does a nice job of this. Mastercam, ooh, I'll have to fix that link. Mastercam is commercial software. FreeCAD has a CAM workbench that was limited, but it's been getting better. And so an option is the CAM workbench in FreeCAD. Then if you're using SolidWorks, there's SolidWorks CAM. And then I'd say Fusion has the most integrated CAM. So in Fusion, seamlessly you go from the CAD to the CAM. And then mods we're going to see when we do PCBs, but mods can do basic toolpaths. So here I'm going to open a part. And so that did the 2D outline, and it's doing multiple passes for the cut depth. And so that produces, I'll talk about the formats in a second, that produces formats. And then mods can also do, this is rough cutting a 3D shape. So what it just did is it made a series of layers to quickly do the rough cutting. And then for a 3D shape, this, and I'll jump ahead, this is showing it's doing the finish cutting, moving all the axes with a fine step over. For formats, ShopBots takes their own format called SBB, and then G-code is by far the most common format. Most of the machines we're using take G-codes. However, and there's a note in the chat, every machine is slightly different in the G-code, and you may need to tweak the G-code commands to match your machine. Now we come to the safety story. This is a tragic article about a Yale student who was working on a machine tool. Her hair got caught in the machine and she died. When I was in grad school, I was working in the machine shop late at night with a fellow grad student. He literally looked over and said, "I'm bored," and then his finger was cut off. Earlier, I told you about mistakes you can make, like uncompressed PNGs, and then I noted you shouldn't do that, and you learn from it. This week, I'll tell you about mistakes, and you can't make them. These are very dangerous. It is safe to do this week's assignment with proper supervision, but the tools you're using can easily cause serious injury. Yeah, this is a link to at MIT, the training we do. The safety training is essential this week. To start, you can get splinters from woods. The chips are sharp. You can get cuts. The tools and the material get very hot. You can get burns. Parts can come flying out. You can get ballistic impacts. And you can set fires. This is the ShopBot at Spinderhallen. They made a mistake. They didn't cut in air. They had the coordinates wrong. And when they cut, the machine cut really deeply, really fast. And they stopped the job. It was screaming. And they thought everything was okay. And then the fire trucks came. What happened was when they made the mistake, they were machining so aggressively that the chips were glowing. They actually ignited them. And the glowing chips went into the dust collector. And the dust collector was full of chips with airflow, and that was a perfect furnace. And so they ignited the dust collector. Once that happens, there's almost nothing you can do about it. And so the dust collector was on fire, flames came out, and they had a huge cleanup and had to replace it. Little end mills, when we make PCBs, when they break, we're just annoyed. These tools, if you break them, sharp shards can go flying at a high velocity. So you always wear safety glasses to protect your eyes. You don't want to have sandals. You want good shoes to protect your toes. You don't want any loose clothes. Your hair has to be tied up. And then depending on what you're handling, you want to wear gloves. You want to always be looking and listening and smelling. When the machine is cutting well, there's a happy cutting sound. It's not quiet. Remember, you need to bite in. It needs to be working, but it's different from the screaming sound it makes when you're doing something wrong. Your hand is not a tool. You never reach in. So one kind of accident is chips are starting to accumulate, and they can actually look pretty, and you reach in to brush them away, and it's actually a hot razor blade, and it slices you. Another is the tool is spinning, and you reach in to slow it down and grab your stock, but it's not held in the stock starts spinning, and it slices your hand. So you're not a tool. You never reach into a power tool. These tools all have emergency stops. Before you turn it on, you have to stop and ask, how do I turn it off? Sounds obvious, but when you panic in an emergency, you want to be clear on how you stop the tool before you start it. And you never do large format machining alone. You want somebody there if there's an accident. And the other thing is, it's like an airplane with a co-pilot. You want eyes and ears. You want somebody to be checking you and you're checking them. You always do this together. And finally, you don't do this when you're tired. You don't do it when you're sleep deprived. You don't do it when you're mad. You need to be at peace. You need to be comfortable. You need to be in a good state to do it. If you're having a terrible day, don't make it worse by making a mistake machining. You need to be well prepared to do this. So safety training is much more important this week, and oversight is going to be much more careful. So do your safety training, then test the run out. How does the kerf differ from the tool? Test the alignment. Is the square part square? Go through the feeds and speeds. Do test cuts in your materials, and then you'll go through the workflow. Then, this link goes to this project where this was making a whole house on a ShopBot snap together. So I want you to design your design, mill, and assemble something big. And the guidance is meter scale. Your project doesn't need to be as big as a meter if you're making, say, a nice laptop stand, but I want you to start from stock on the order of, meter scale stock, because this week's assignment is all about fixturing feeds and speeds. Then try to avoid fasteners or glue. Try to use joints. And then extra credit is don't just have flat surfaces, play with flexures and kerfing and see if you can bend in 3D, not just make flat things in 2D. Last note is you're going to be very limited by time on the machine. So don't spend many days doing the design and then pile up. You'll fail this week if you all pile up and try to do your machining on Tuesday. Give yourself a day or two to design, but then you need to get in and start machining to get through the week. Okay, at the end of this week, the goal is you should be liberated. You should feel like you don't need to buy furniture. You can make furniture. You can make the kinds of things you see around you on a much bigger scale. So, as usual, Saturday time, make good use of it. Monday recitations, sustainable materials plus a supplement. And then next week we'll actually be finally making electronics. So this is a very creative week, but it needs good time management. I look forward to see your big things. Happy machining.
Bye.
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 Takk fyrir Kjella.
Bye, thanks.
Wiedersehen.
Bye.
Bye.
Bye.